Hello everyone, I'm Xinyi. Sorry for not attending conference in person today. I prepared this video to introduce our work, AtomicDisk, a secure virtual disk against eviction attack. I will start by providing some essential background information. Then we will talk about the eviction attacks that we have identified. Following that, I will introduce the key design of AtomicDisk. And finally, I will show the evaluation result and our conclusions. Nowadays, trust execution environment or TEs are widely used in cloud environments. They can protect sensitive code and data from privileged adversary outside, like host operating system, hypervisor, and other applications. Now let's define our threat model. First, we trust TE hardware and software like Intel SGX to protect confidentiality and the integrity of memory and CPU. Therefore, we place our trust in all software executing within the TE boundaries. However, we must also consider powerful adversaries within our cloud environment. They are privileged, online, and active. This means they possess several critical capabilities. They have complete control over all host resources outside TE. They can launch attack at any point during TE execution. They can manipulate any I/O request and response between the TE and the host block device. This leads us to a critical point: is that TE lacks I/O protection, and this is why a secure virtual disk is essential. It addresses the critical I/O protection gap we just discussed. The secure virtual disk can protect the disk I/O of TE by providing these security attributes, and it can free the file system from worrying about TE security risks. And it can also simplify security analysis and reasoning because it only provides simple interface like read, write, sync. Let's now explain the security attributes we mentioned before. To counter such a strong adversary, the secure virtual disk should provide a minimal security guarantees of confidentiality, integrity, freshness, and consistency. Confidentiality protects written data from unauthorized access. Integrity guarantees that data is not tampered or corrupted. Freshness prevents replete attack and ensures the latest data is always provided. Consistency maintain data consistency even after system crashes. On Linux, the state-of-art solution is device mapper by using a combination of DM crypt and DM integrity. However, this setup only addresses confidentiality and integrity. On Intel SGX, SGX-PFS deliver all four attributes: confidentiality, integrity, freshness, and consistency, or CIFC for short. Now let's dive into how the state-of-art solution Intel SGX-PFS delivers those CIFC security attributes we discussed. SGX-PFS is built around three key components: a modified Merkle Hash Tree or MHT, a fixed set cache, and a journal. To achieve both confidentiality and integrity, Intel has enhanced the classic MHT by employing authenticated encryption. In detail, each internal MHT node stores the encryption key and the message authentication code or MAC of his child node. Freshness is ensured through MAC chain verification, guaranteeing the latest data. The cache residing within secure memory stored metanode MHT nodes, data nodes, boosting I/O performance. And finally, the journal maintains the previous version of 30 nodes before eviction, thereby ensuring consistency. These three components work together, allowing SGX-PFS to achieve all four CIFC security attributes. Before we delve into eviction attacks, let's clarify the concept of snapshots and unanticipated snapshots. We define snapshots as a persistent system state at a specific time. Think of Docker container snapshot, where file chains are saving using Docker commits. Similarly, enclaves also have snapshots, which are protected files that preserve the enclave states. Unanticipated snapshots are snapshots not expected by the application logic. Let's consider SGX-PFS as an example. Imagine an application within an enclave writing a series of data blocks to SGX-PFS protect file. Ideally, from the application viewpoint, these blocks should be written and persist as a single unit. However, here is where the problem arises. When the cache within SGX-PFS reaches its capacity, it initiates an eviction process. The eviction leads to the creation of a partial persistent state, which is blocked from B1 to B4. And this is what we define as an anticipated snapshot. Subsequently, when a single command is executed, the complete and consistent snapshot are expected by the application is created, which is blocks from B1 to B8. In normal environment, these eviction-generated snapshots are harmless, but in TEs, these snapshots are vulnerable. Now let's break down the three primary reasons why these unanticipated snapshots are vulnerable within TEs. Firstly, they can generate it by TEs because the POSIX standard put little constraint on the ordering and atomicity guarantees, allowing the cache layer of TE to perform eviction at any time. Secondly, they can captured by adversary because adversary control everything outside enclaves, including monitor all I/O. Thirdly, and perhaps most critically, these captured snapshots can be replayed by the adversary. A snapshot that generated by SGX-PFS share the same root key, so the enclave cannot distinguish them. To illustrate the practical implication of these vulnerabilities, let's examine a concrete attack using Redis as our example. Deploying a Redis service typically involves two essential steps. First, creating and initializing a Redis configuration file if it doesn't already exist. Secondly, start the Redis server to handle user requests. Now, the eviction attacks unfold in 4 key stages. During the first step, SGX-PFS, due to the MHT cache eviction, generates unanticipated snapshot. Critically, this snapshot may lack the necessary password requirements. The adversary can control over the environment outside the enclaves, captures these vulnerable snapshots, and then the adversary can restart or initialize a new enclave using these snapshots. So consequently, the adversary gains complete unauthorized access to the Redis server, bypassing any authentication mechanism. And it's practical to explore this unanticipated snapshot to attack more applications. Popular databases like MongoDB and Cassandra use similar configuration-based authentication. And more interesting, unanticipated snapshot can involve multiple files. We leave it for future work. To prevent eviction attacks, we propose a new security attributes named sync atomicity. These attributes guarantees that all evicted write before a sync are committed in an all or nothing manner. And as we can see, AtomicDisk is the only security solution that achieves all security attributes. To achieve sync atomicity, we have developed AtomicDisk by extending SGX-PFS with the following key modification. Firstly, we have introduced a dual state system for data blocks, committed and uncommitted. This allows us to track the commitment status of disk image. And we introduced an operation called commit to transaction blocks from uncommitted to committed. Thirdly, we have refactored the recovery procedure upon reboot. AtomicDisk can now identify and reject any uncommitted writes. The commit operation transaction all data blocks of disk image to committed state. To support this, we extend the PFS metadata node with a committed flag. By default, the flag is set to false. As shown in the figure, the commit operation is triggered by a user initiate sync and proceeds as follows. Firstly, it executes the standard PFS flush procedure, which involves writing dirty nodes to the journal and flushing them to persistence storage. Secondly, it updates the committed flag to true and flushes the modified metadata node to the disk. This signifies that the entire disk image has now been committed. And finally, as the journal is no longer required for recovery, it can safely delete it. Conversely, the internal flush operation may be triggered by a write command, sets the committed flag back to false. This indicates that the disk image represents an anticipated snapshot generated as a result of cache eviction. If the flag is set to false, indicating an uncommitted state, the disk image cannot be opened directly. Instead, we rely on the journal to recover the disk image to the latest synchronized states. Within the journal, each block are assigned one of two status, committed or uncommitted. Block's first appearance in the journal is marked as committed because the journal stores the previous version of block. This signifies either a new write to an empty block or the first overwrite of a committed block. Subsequent overwrites of the same block within the journal are then marked as uncommitted. During the recovery process, AtomicDisk reads the journal from its beginning to the end for each logical block encountered for the first time, which, as we discussed, is marked as committed. AtomicDisk restores these blocks to the disk image. An in-memory bitmap is used to record and restore blocks and identify the subsequent uncommitted blocks. Upon completion of journal replay, AtomicDisk updates the committed block to true, and then all data blocks within the disk image has been successfully committed. Now we talk about the evaluation. We compare AtomicDisk with two baseline, PFS disk and crypt disk. PFS disk is a secure block device redirecting I/O to a SGX protected file. And the PFS and the crypt disk is a mirror version of Linux DM in SGX. Firstly, we show the security results. We use trace-driven benchmarks where each trace concludes with a single sync request. As we can see, AtomicDisk only generates one valid snapshot caused by the sync, and the PFS disk generates hundreds of thousands of snapshots per trace, thus being vulnerable to eviction attacks. Now let's move on the performance evaluation. The FIO configuration is listed here. In FIO benchmark, AtomicDisk and PFS disk had similar write performance as AtomicDisk save both committed and uncommitted block to the journal, thus having the same write amplification as PFS disk. AtomicDisk and PFS disk also have similar read performance because they process read requests exactly the same. Crypt disk outperformed because it only performed data encryption without a MHT structure, avoiding write amplification, but lacking freshness and consistency. In trace-driven benchmark, the results are similar to FIO, while the performance gap narrows as these workloads are dominated by small I/O operation. And in the end is a YCSB benchmark. We choose two applications, Redis and BedgerDB. which is an Ellipson tree-based key-value store. For Redis, all three disks achieve similar performance due to Redis lightweight I/O patterns. And for BetterDB, the gap for BetterDB, AtomicDisk and PFS still achieve similar performance. The gap between AtomicDisk and CryptoDisk narrowed due to its uniform read distribution, causing frequent small random reads that bottleneck the performance of CryptoDisk. In summary, firstly, we identified eviction attacks, a new type of attacks against Intel SGX. Second, we have introduced sync atomicity, formal security properties as a fundamental defense mechanism against eviction attacks. Third, we have developed AtomicDisk, a secure virtual disk that achieves sync atomicity while maintaining SGX-PFS comparable performance. Thank you for listening. AtomicDisk has been open sourced on GitHub. You can check the link here for more details. If you have any questions, please contact me. That's all. Thanks.